So now the next part of the lecture of the overview of artificial intelligence, we come to expert systems and knowledge representation. So in expert systems and knowledge representation, we have rule-based systems, systems that use if-then rules to make decisions. Now then there are semantic networks, these are ways to represent knowledge using connected concepts. So it is representing knowledge using connected concepts. Then there are frames and scripts. So rule based systems, semantic networks, frames and scripts, structures for organizing complex information. So these organizes complex information. Then comes ontology engineering. It is about building models that define the relationships among the concepts. Description logic, a family of languages used to describe and reason about concepts. So very important, description logics. So rule-based systems in expert system knowledge representation, rule-based systems, semantic networks, frames and scripts, ontology engineering, description knowledge, logics, then knowledge graphs. So networks of interconnected information like a web of facts, then inference engines, systems that apply logical rules to knowledge to deduce new information. So important. Next comes logic programming. In logic programming, we have Prolog, it's a programming language based on formal logic. So that is about expert systems and knowledge representation. Rule-based systems, semantic networks, frames and scripts, ontology engineering, description logics, knowledge graphs, inference engines, logic programming. Then comes very important topic, fuzzy logic and probabilistic models. So fuzzy sets and fuzzy inference systems. So fuzzy sets, in it we have fuzzy sets and fuzzy inference systems. It's handling reasoning that is approximate rather than exact. So, and then there comes Bayesian networks. These are graphical models, graph theoretical models that represent variables and their probabilities. Then we have Markov models, which are models where the next state depends only on the current state. So, next state depends only on the current state. Then hidden Markov models where the states are not directly visible. Markov decision processes, these are models for decision making where outcomes are partly random. Outcomes are partly random. Then probabilistic graphical models, models that use graphs to represent and compute with complex probabilities. So in fuzzy logic and probabilistic models, we have fuzzy sets and fuzzy inference systems for approximate reasoning, then Bayesian networks with the variables and probabilities, Markov models where next state depends only on the current state, then hidden Markov models, states are not directly visible, Markov decision processes where outcomes are partly random, and probabilistic graphical models. Then comes evolutionary computation and optimization. So we have genetic algorithms that mimic natural selection to find good solutions. Genetic programming Using evolutionary processes to evolve programs or expressions. Using evolutionary processes to evolve programs or expressions. It's very interesting. Genetic programming. Then evolutionary strategies, optimization techniques inspired by biological evolution, very widespread. Then swarm intelligence. This is particle swarm optimization. So finding the best solution by simulating a group solution by it's a best solution finding, simulating a group moving around in the problem space. Ant colony optimization. These are all on swarm optimization. So finding paths through graphs by simulating the behavior of ants finding paths to food. Then simulated annealing, an optimization method that simulates the cooling of metal to find low energy states, good solutions. Stochastic optimization, optimization that incorporates randomness. Then differential evolution, an algorithm for finding optimal solutions by iteratively improving. So here in evolutionary computation and optimization, we have genetic algorithms using natural selection, genetic programming to evolve programs or expressions, evolutionary strategies, then swarm intelligence. We have then swarm intelligence. In it, we have particle swarm optimization, and colony optimization. Then simulated annealing, an optimization method that simulates the cooling of metal to find low energy states, good solutions. An optimization method that simulates the cooling of metal to find low energy states. Then stochastic optimization and differential evolution. Then comes reinforcement learning, policy gradient methods. So techniques for optimizing the policy, the way actions are chosen directly. Very, very important. Then comes Q learning, learning the value of state. Here actions are chosen. Learning the value of action in a state to optimize behavior. So it is learning the value of action in a particular state. Then deep Q networks. These are using deep learning to approximate Q values. Deep learning to approximate Q values. So in Q learning is the value of action in a state, and in deep Q networks is approximating the Q values using deep learning. Then actor critic methods, combining policy and value learning. Very, very interesting and important. Then multi-agent reinforcement learning, multiple agents learning and interacting in the same environment. Multiple agents learning and interacting in the same environment. So that is multiple agent reinforcement learning. Inverse reinforcement learning, learning the reward function by observing behavior. Learning the reward function by observing behavior. Learning the reward function by observing behavior. So it is learning the reward function itself. Inverse reinforcement learning. It is learning the reward function itself by observing the behavior. Very, very interesting. Inverse reinforcement learning. Now, exploration versus exploitation dilemma, very fundamental. Deciding between trying new things and sticking with known rewarding actions. So very very fundamental thing. So in reinforcement learning, we took the overview of policy gradient methods. So way actions are chosen, optimizing the policy. Q learning, the well learning the value of action in a state. Deep Q networks using deep learning to approximate the Q values. Actor critic methods very interesting, combining policy, actor, and value critic learning. Multi-agent reinforcement learning, where multiple agents learning and interacting in the same environment. Then inverse reinforcement learning, learning the reward function by observing behavior. Inverse reinforcement learning, learning the reward function by observing behavior. It is learning the reward function by observing behavior. Very, very interesting. Exploration versus exploitation dilemma, very fundamental concept, deciding between trying new things and sticking with known rewarding actions. So I think, can we cover cognitive computing? Yeah, I think we can cover computing a little bit faster. So, cognitive computing and neuroscience, next topic. So, we have cognitive architectures. So, a model designed to emulate human cognitive processes. Another cognitive architecture, the models human cognition ACTR. Neuromorphic computing, designing hardware that mimics the neurobiological architectures present in the nervous system. Very, very interesting. So, it is mimicking the neurobiological architectures present in the nervous system. Brain computer interfaces, systems that allow direct communication between the brain and the external device. Spiking neural networks, very important concept. Neural networks that model neurons more closely by simulating the spikes of activity. So, that is about all in cognitive computing. Uh, I think we can cover multi-agent systems also. So in multi-agent systems, agent-based modeling is there. It is simulating the actions and interactions of autonomous agents. Actions and interactions of autonomous agents. Distributed AI systems where multiple agents work in different locations but towards a common goal. Locations are different. Cooperative and competitive agents, agents that either work together or compete in their environment. Negotiation and coordination, agents communicating and making decisions together, very very interesting and important also. Communicating and making decisions together, negotiation and coordination. Game theory applications, using mathematical models to study strategic interactions. Swarm intelligence, collective behavior of decentralized systems. So that is all uh, for this video. Yes, so that is all for this video. We'll continue in the next video.